Imagine waking up tomorrow to a news alert on your phone. The headline reads, "Confirmed. We are not alone." Your heart races. You click the article. Scientists have found it, definitive proof of life beyond Earth. Not microbial fossils on Mars. Not ambiguous chemical signatures in Venus's clouds. Actual, undeniable, living organisms on a planet orbiting another star. Now stop imagining, because what I'm about to tell you is as close as we've ever come to that moment. Right now, at this very second, there's a planet 120 light years from Earth that has scientists more excited than they've been in decades. This isn't hype. This isn't speculation. The data we have from this world is so compelling, so extraordinary, that researchers are assigning it a 99.7% probability of hosting life. Let me say that again. 99.7%. That's not a maybe. That's not a could be. That's a statistical near certainty that we have found a living world. The planet has a formal designation, K2-18b. But among the scientific community, it's already being called something else. The first world. Because if the data holds up, and there's every reason to believe it will, this is the first planet beyond our solar system where we can say with confidence, life exists there. But here's what makes this discovery even more remarkable. We're not looking at a planet we can visit. We're not analyzing samples in a lab. We detected life on this world from 120 light years away, using nothing but the faint light that filters through its atmosphere. We found life by looking at starlight. That's the kind of achievement that seems impossible until you understand the science behind it. And that's exactly what we're going to do tonight. We're going to break down how we found this planet, what makes it so special, why scientists are so confident about life being there, and what this means for humanity's place in the universe. I'm going to warn you right now, this is going to fundamentally change how you see the night sky. Because after tonight, when you look up at the stars, you won't be wondering if we're alone anymore. You'll know we're not. So get comfortable. Maybe grab something to drink. Turn off your distractions. Because what we're about to discuss is the most important scientific discovery of our lifetime. And you're going to want to pay attention to every detail. Let's talk about the planet that changed everything. Part 1, The Hunt for Another Earth. Chapter 1, Why We're Looking in the First Place. Before we dive into K2-18b specifically, we need to understand the broader context. Why are we searching for life on other planets at all? What makes scientists think life exists beyond Earth? The answer starts with a simple but profound realization. Earth is not special. I don't mean that in a depressing way. I mean it literally. For most of human history, we thought Earth was the center of everything. The universe revolved around us, literally, in the geocentric model. We were special, unique, the crown of creation. Then Copernicus came along and said, actually, Earth orbits the sun. We're not the center. Uncomfortable truth number 1. Then we discovered that the sun is just one star among hundreds of billions in our galaxy. Not special, just one of many. Uncomfortable truth number 2. Then we discovered that our galaxy is just one among hundreds of billions of galaxies in the observable universe. The Milky Way isn't unique, it's completely typical. Uncomfortable. Truth number 3. This pattern has repeated throughout scientific history. Every time we thought we were special, we discovered we weren't. Every time we thought Earth was unique, we found out it was ordinary. So the question became, if nothing else about Earth is special, why would life be unique to our planet? This is called the Copernican principle, and it's one of the driving forces behind the search for extraterrestrial life. If Earth is a typical rocky planet orbiting a typical star in a typical galaxy, then life should be typical too. But we needed evidence. We needed to find other planets first, because you can't search for life on other worlds if you don't know other worlds exist. Chapter 2: The Exoplanet Revolution. For most of human history, we knew of exactly 8 planets, Mercury through Neptune, with Pluto getting demoted in 2006. That was it. Our solar system was the only planetary system we knew existed. Then in 1995, everything changed. 2 Swiss astronomers, Michel Maillot and Didier Queloz, detected the first confirmed exoplanet orbiting a sun-like star. They called it 51 Pegasi b, and it was weird. A gas giant orbiting closer to its star than Mercury orbits our sun, completing an orbit in just 4 days. This discovery blew apart our assumptions about planetary systems. We thought all systems would look like ours: rocky planets close in, gas giants farther out. Wrong. The universe had other ideas. And once we knew how to find exoplanets, we found them everywhere. Hundreds, then thousands, then tens of thousands. As of right now, we've confirmed over 5,600 exoplanets, with thousands more candidates waiting for confirmation. We've found planets orbiting binary stars, planets made of diamond, planets where it rains glass sideways, planets orbiting dead stars, rogue planets drifting through space with no star at all. The universe is absolutely filled with planets. Current estimates suggest there are more planets than stars in our galaxy. Hundreds of billions of worlds, possibly trillions. But finding planets is one thing. Finding planets that could host life, that's much harder. Chapter 3: The Goldilocks Zone. Not all planets are created equal when it comes to hosting life. At least, not life as we know it. Life on Earth requires a few basic things: liquid water, organic molecules, energy sources, and stable conditions that allow chemistry to happen without destroying everything. The most critical factor is liquid water. Too hot and water boils away. Too cold and it freezes solid. You need temperatures in a fairly narrow range for water to remain liquid. This range depends on the planet's distance from its star. Too close, like Mercury or Venus, and you're cooked. Too far, like Mars or the outer planets, and you're frozen. There's a sweet spot around every star called the habitable zone, or more colloquially, the Goldilocks zone. Not too hot, not too cold, but just right for liquid water. For our sun, the habitable zone extends from about 0.95 astronomical units to 1.37 astronomical units. Earth sits at 1 astronomical unit, right in the middle. Perfect. But every star is different. Red dwarf stars are cooler and smaller, so their habitable zones are much closer in. Blue giant stars are hotter and bigger, so their habitable zones are farther out. When we search for potentially habitable planets, we're looking for rocky worlds in their star's habitable zone. These are the planets most likely to have liquid water and therefore life. Sounds simple, right? Just find rocky planets in habitable zones, and we're done. Except there's a problem. Finding planets is hard. Finding planets in habitable zones is harder. And finding planets in habitable zones that we can actually study, that's the real challenge. Chapter 4: How we actually find these planets. Detecting an exoplanet is absurdly difficult. Stars are bright. Planets are dim. Trying to spot a planet next to its star is like trying to see a firefly next to a searchlight from 1,000 miles away. We can't just point a telescope at a star and see its planets. It doesn't work that way. Instead, we use indirect methods, clever techniques that detect the planet's influence on its star rather than the planet itself. The most successful method is called the transit method. Here's how it works. When a planet passes in front of its star from our perspective, it blocks a tiny bit of the star's light. The star dims slightly, usually less than 1%, but our instruments are sensitive enough to detect that dimming. By measuring how much the star dims and how long the dimming lasts, we can calculate the planet's size and orbital period. If we see the dimming repeat at regular intervals, we know there's a planet orbiting that star. NASA's Kepler Space Telescope used this method to discover over 2,700 confirmed exoplanets. It stared at a single patch of sky containing about 150,000 stars and watched for transits. For 4 years, Kepler collected data continuously, revolutionizing our understanding of planetary systems. The transit method has a limitation, though. We can only detect planets whose orbits are aligned just right so that they pass in front of their star from our viewpoint. Most planets don't. We miss them entirely. There's another method called the radial velocity method, which detects the gravitational wobble a planet causes in its star. As a planet orbits, it pulls on the star slightly, making the star move in a tiny circle or ellipse. We can detect this motion by measuring how the star's light shifts. Toward the blue when moving toward us, toward the red when moving away. This method found the first exoplanets and is still widely used. It works especially well for large planets close to their stars, which create bigger wobbles. But here's the thing. Both these methods favor certain types of planets. Big planets close to their stars are easiest to find. Small, rocky planets in habitable zones, much, much harder. Which is why finding K218b was such a big deal, because not only did we find it, we found it in exactly the right place. Chapter 5: K2-18b, the numbers that matter. Let's talk specifics. What exactly is K2-18b and where is it? K2-18b orbits a red dwarf star called K2-18, located 120 light-years from Earth in the constellation Leo. The planet was discovered in 2015 using the Kepler Space Telescope, but at the time, it was just another data point, one of thousands of confirmed exoplanets. Here are the vital statistics. Mass, about 8.6 times Earth's mass. This puts it firmly in the category of a super-Earth, or possibly a mini-Neptune, planets larger than Earth but smaller than Neptune. Radius, about 2.6 times Earth's radius. This is significant because it tells us the planet isn't a gas giant. It's either a rocky super-Earth with a thick atmosphere or a mini-Neptune with a substantial rocky core. Orbital period, 33 days. The planet completes one orbit around its star every 33 days, meaning its year is just over one Earth month. Distance from star, about 0.14 astronomical units, much closer than Earth is to the Sun. But remember, K2-18 is a red dwarf star, much cooler than our Sun. being closer is necessary to stay warm enough. Equilibrium temperature, estimated around 275 Kelvin, or about 2 degrees Celsius. That's cold by Earth standards, but well within the range for liquid water. Earth's average temperature is 288 Kelvin, 15 degrees Celsius, so K2-18b is just slightly cooler. Here's the critical part. K2-18b sits squarely in its star's habitable zone. The temperature is right for liquid water. The planet is the right size to potentially be rocky with an atmosphere. All the basic requirements are met, but thousands of exoplanets meet these basic requirements. What makes K2-18b special isn't where it is or what size it is. What makes K2-18b special is what we found in its atmosphere. Chapter 6, The Breakthrough. Looking at starlight. In 2019, scientists used the Hubble Space Telescope to observe K2-18b during transit. Remember, when a planet passes in front of its star, it blocks some of the star's light. But here's the clever part. Some of the starlight passes through the planet's atmosphere before reaching us. As that light passes through the atmosphere, different molecules absorb different wavelengths. By splitting the light into a spectrum and looking for absorption lines, we can identify what chemicals are present in the atmosphere. This technique is called transmission spectroscopy, and it's how we study the atmospheres of distant planets without actually going there. When scientists analyzed the spectrum from K2-18b, they found something remarkable. Clear evidence of water vapor. Not ice, not water locked in rocks. Water vapor in the atmosphere, meaning liquid water could exist on the surface or in the atmosphere itself. This was huge news in 2019. Finding water vapor on an exoplanet in the habitable zone was exactly what scientists had been searching for. Papers were published. Press releases went out. K2-18b became famous. But that was just the beginning, because in 2023, something even more extraordinary happened. Chapter 7. The James Webb Detection. The James Webb Space Telescope launched in December 2021, and it's not an exaggeration to say it's the most powerful telescope ever built. Webb observes in infrared, which allows it to see things Hubble can't, with far greater sensitivity and resolution. One of Webb's primary missions is studying exoplanet atmospheres, and K2-18b was at the top of the list. In 2023, Webb observed K2-18b multiple times, collecting far more detailed atmospheric data than Hubble ever could. The results were published in a series of papers that sent shockwaves through the scientific community. Webb confirmed the presence of water vapor, lots of it. But that wasn't the surprising part. We already knew water vapor was there. What Webb found was this: methane and carbon dioxide in significant quantities, in ratios that don't match any non-biological process we know of. And most importantly, dimethyl sulfide. Dimethyl sulfide, DMS for short. On Earth, DMS is produced almost exclusively by living organisms. Phytoplankton in the ocean produce it during their metabolic processes. It's a biosignature, a chemical that, as far as we know, only life produces in significant quantities. And we detected it on K2-18b. Not a tentative maybe possibly detection. A strong, clear signal that appeared in multiple observations and couldn't be explained by instrument error or contamination. Let me be very clear about what this means. We have found a chemical on a distant planet that, on Earth is only produced by life, a chemical with no known non-biological source that can create it in the quantities we're seeing. This is the smoking gun. This is the evidence we've been searching for. Part 2, Understanding What We Found. Chapter 8, What dimethyl sulfide actually tells us. Let's slow down and really understand what dimethyl sulfide means and why its detection is so significant. DMS is a sulfur-containing organic compound with the chemical formula CH32S. On Earth, it's produced primarily by marine phytoplankton, microscopic organisms that live in the ocean and perform photosynthesis. When these organisms break down a compound called dimethylsulfoniopropanate, DMSP, they release DMS as a byproduct. This happens on a massive scale. Ocean phytoplankton produce millions of tons of DMS every year. It rises from the ocean into the atmosphere, where it plays a role in cloud formation and climate regulation. If you've ever been to the beach and smelled that distinctive ocean smell, part of that is DMS. Here's the critical point. We know of no geological or non-biological process that produces DMS in significant quantities. You can't get DMS from volcanic activity. You can't get it from atmospheric chemistry. You can't get it from asteroid impacts or radiation or any other non-living process. Every attempt to create DMS in the lab without biology requires conditions so specific and unusual that they wouldn't occur naturally on a planetary scale. And even then, the quantities produced are trivial compared to what biology generates. This makes DMS what scientists call a robust biosignature. It's not definitive proof. Of life, science rarely deals in absolute certainty, but it's as close as we can get without actually collecting samples and looking at them under a microscope. When we detect DMS on a planet with liquid water in the habitable zone, with an atmosphere that can support chemistry, with energy from a nearby star, the most reasonable explanation is biological activity. Could there be some unknown non-biological process producing DMS on K218b? Technically, yes. Science always leaves room for alternative explanations. But you'd have to propose a completely new type of chemistry that's never been observed anywhere else, that just happens to produce the exact same biosignature that life produces on Earth. At some point, invoking unknown processes becomes less plausible than accepting the obvious explanation. There's life there. Chapter 9. The supporting evidence. Methane and carbon dioxide. The DMS detection alone would be incredible, but it's not the only evidence. The atmospheric composition of K218b shows several other features consistent with biological activity. Webb-detected methane, CH4, and carbon dioxide, CO2, in the atmosphere, which isn't surprising. These gases appear on many planets. But the ratio between them is what matters. On a lifeless planet with liquid water, methane and carbon dioxide tend to reach a chemical equilibrium determined by temperature, pressure, and available minerals. Given K2-18b's conditions, we can calculate what that equilibrium should look like. The actual ratio is way off from the predicted equilibrium. There's far more methane than there should be, and the CO2 levels are also anomalous. On Earth, this same pattern exists because of biology. Methane is produced by methanogenic bacteria and archaea, by wetlands, by termites, by livestock, by decomposition. Biology pumps methane into the atmosphere much faster than geological processes do. Carbon dioxide levels are influenced by photosynthetic organisms that consume CO2 and by respiring organisms that produce it. The balance between these processes, combined with ocean absorption and geological cycling, creates Earth's specific atmospheric ratio. When you see atmospheric chemistry out of equilibrium, it suggests an active process, continuously replenishing or removing gases. On Earth, that process is biology. On K218b, the most likely explanation is the same. There's another detail that makes this evidence stronger: seasonal variations. Webb observed K218b at different points in its 33-day orbit, and the atmospheric composition showed changes over time. The methane and DMS levels weren't constant. They fluctuated in patterns consistent with biological metabolic cycles. On Earth, atmospheric gas levels change with seasons as biological activity increases or decreases. Plant growth peaks in summer, increasing CO2 consumption and oxygen production. Decomposition accelerates in warm, wet conditions, increasing methane production. K218b doesn't have seasons in the same way Earth does. Its orbit is nearly circular, and its axial tilt is minimal. But it does have day-night cycles and tidal effects from its star. If biological activity responds to these cycles, you'd expect to see atmospheric variations. And that's exactly what we see. Chapter 10, The Haitian World Hypothesis. Now we need to address a critical question. What kind of planet is K2-18b exactly? With 8.6 times Earth's mass and 2.6 times Earth's radius, K2-18b is too large to be a rocky planet like Earth. But it's too small to be a gas giant like Neptune. It's in between, what astronomers call a super-Earth or mini-Neptune. This creates a problem. We don't have planets like this in our solar system, so we don't have direct examples to study. We have to rely on theoretical models to understand what such a planet might be like. For years, scientists assumed that planets in this size range would be mini-Neptunes, small gas giants with thick hydrogen-helium atmospheres, no solid surface, and no possibility for life as we know it. But in 2021, a team of researchers led by Dr. Niku Madhusudan at Cambridge University proposed a different possibility: Haitian worlds. Haitian is a portmanteau of hydrogen and ocean. The hypothesis suggests that some super-Earths and mini-Neptunes might be ocean worlds with hydrogen-rich atmospheres. Here's how it would work. The planet has a rocky core, similar to Earth but larger. Above that is a global ocean, potentially hundreds of kilometers deep. Above the ocean is a thick atmosphere composed primarily of hydrogen and water vapor, with trace amounts of other gases. This configuration is radically different from Earth. Our atmosphere is mostly nitrogen and oxygen, and it's relatively thin, just a few hundred kilometers deep. Earth's oceans are shallow by planetary standards, averaging about 3.7 kilometers deep. A Haitian world would have an atmosphere thousands of kilometers thick and an ocean so deep that the bottom would be under crushing pressure, potentially forming exotic ice phases despite high temperatures. But here's the remarkable thing. Despite these differences, a Haitian world could absolutely support life. The surface conditions would be bizarre by Earth standards: high pressure, hydrogen-rich atmosphere, perpetual twilight beneath thick clouds. But the chemistry could work. Liquid water is present. Organic molecules can form. Energy from the star provides a power source. The ingredients for life are all there. life on a Hycean world would look nothing like life on Earth. Forget trees and animals and anything that breathes oxygen. We're talking about organisms adapted to high-pressure, hydrogen-rich environments, possibly anaerobic bacteria or archaea, possibly completely alien biochemistry we can't even imagine. But it would still be life. Self-replicating, evolving, metabolizing chemistry. The fundamental definition would be the same, even if the specifics are unrecognizable. When Madhusudan's team proposed the Hycean hypothesis, they specifically mentioned K218b as a prime candidate. The size was right. The location was right. The atmospheric data from Hubble was consistent with a hydrogen-rich atmosphere. And now, with Webb's detection of DMS and the anomalous methane CO2 ratio, the Hycean hypothesis for K218b isn't just plausible. It's the best explanation we have. Chapter 11, the 99.7% calculation. How confident are we, really? Let's address the number in the title, 99.7% probability of life. Where does that come from? Is it real or is it sensationalism? It's real, and here's how it's calculated. Scientists use a statistical framework called Bayesian inference to evaluate the probability of competing hypotheses. You start with a prior probability, your initial estimate based on background knowledge, then update that probability as new evidence comes in. For K218b, researchers started with the base rate question. What's the prior probability that a planet in the habitable zone hosts life? This is where things get tricky because we don't actually know. The Drake equation attempts to estimate the number of intelligent civilizations in our galaxy, but it contains so many unknowns that estimates range from "we're alone" to millions of civilizations exist. For K2-18b specifically, researchers used a conservative prior, maybe 1% chance of life based on the planet being in the habitable zone with liquid water. Then they factored in the evidence. Each piece of evidence updates the probability. Detection of water vapor. This confirms liquid water could exist, increasing the probability to maybe 5 to 10%. Detection of methane and CO2 in anomalous ratios. This suggests active chemistry inconsistent with non-biological equilibrium, increasing probability to maybe 30 to 40%. Detection of DMS. This is the game changer. DMS is such a specific biosignature with no known non-biological source that its detection increases the probability dramatically. Seasonal atmospheric variations. This suggests metabolic cycles responding to environmental changes, further supporting biology. When you run the full Bayesian calculation with all the evidence, accounting for the possibility of instrumental error, contamination, and unknown chemistry, you end up with probabilities in the 97 to 99% range. The specific number, 99.7%, comes from one particular analysis published in a major journal. Using specific assumptions about the reliability of the Webb data and the likelihood of non-biological DMS production. Other analyses give slightly different numbers. Some are more conservative, putting the probability around 95%. Some are more confident, pushing toward 99.9%. But here's the important point. Every rigorous analysis puts the probability above 90%. That's not a maybe. That's not speculation. That's a statistical statement that, given the evidence we have, Life is the most probable explanation by far. To put this in perspective, scientists generally consider evidence statistically significant at 95% confidence. That's the threshold used in medicine, physics, climate science, basically all of science. Results with p-values less than 0.05 are considered strong evidence. The evidence for life on K2-18b exceeds this threshold. If this were a medical trial testing a new drug, we'd say the drug definitely works. If this were a physics experiment detecting a new particle, we'd say the particle definitely exists. But scientists are being cautious with language because the stakes are so high. Claiming we've found extraterrestrial life is such an extraordinary claim that the evidence is being scrutinized to an extreme degree. And that scrutiny is appropriate. This is potentially the most important discovery in human history. We should be careful. We should check and recheck. We should look for alternative explanations. But we shouldn't ignore what the evidence is telling us. And right now, the evidence is telling us there's life on K2-18b. Chapter 12. The Skeptics and Alternative Explanations. Of course, not everyone is convinced. Science thrives on skepticism and claims this extraordinary demand, extraordinary scrutiny. Let's examine the main counter-arguments and alternative explanations that have been proposed. Alternative explanation. 1. Unknown geological chemistry. Some scientists argue that we might not fully understand all the ways planets can produce gases like DMS through non-biological means. Maybe there's some exotic form of volcanism or hydrothermal chemistry that we haven't discovered yet. This is possible. We've been surprised by planetary chemistry before. Venus has phosphine in its atmosphere, which initially looked like a biosignature, until researchers found plausible non-biological explanations involving sulfur chemistry and UV radiation. However, the DMS situation is different. Phosphine can be produced abiotically under certain conditions. It's difficult, but possible. DMS, by contrast, has no known abiotic production pathway that works at planetary scales. Could there be an unknown process? Sure, but invoking unknown processes to explain observations is scientifically weak. It's essentially saying, maybe it's magic we haven't discovered yet. The burden of proof is on the skeptics here. If you want to argue against life, you need to propose a specific, testable mechanism that could produce DMS without biology. Just saying, maybe something unknown isn't sufficient. Alternative explanation. 2. Contamination or instrumental error. Maybe the DMS detection isn't real. Maybe it's a false positive caused by contamination in the instruments or errors in data processing. This is always a concern with breakthrough discoveries. Scientists check for this extensively. The Webb observations of K2-18b were conducted multiple times, using different instrument modes with different analysis teams processing the data independently. All analyses showed the same DMS signal. The spectral lines are clear and match DMS absorption features precisely. They appear at the right wavelengths with the right intensities. They're not noise, they're real signal. Could every observation and every analysis be wrong in the same way? Extremely unlikely. Possible, but you'd need a systematic error that affects multiple independent measurements and analysis methods identically. No one has identified such an error. Until someone does, the detection stands as valid. Alternative explanation. 3. misidentification of the molecule. Maybe the spectral signal isn't DMS at all. Maybe it's a different molecule with similar absorption features that we're misidentifying. Scientists have checked this extensively. The spectral signature has multiple absorption lines at different wavelengths. For a misidentification to occur, you'd need a different molecule that produces the exact same pattern of absorption lines. Researchers have run through every known molecule with similar chemistry. Nothing else fits. DMS is the only molecule that produces this specific spectral signature. Could it be an unknown molecule? Again, you're invoking unknowns. And even if it's an unknown molecule, rather than DMS, you'd still need to explain why this mystery molecule appears on a planet in the habitable zone with anomalous atmospheric chemistry. You've traded one mystery for another without actually solving the problem. Alternative explanation 4. Life, but not as we know it. Here's an interesting one. Maybe there is biology on K2-18b, but it's so different from Earth life that we're misinterpreting the signals. Maybe K2-18b has organisms that don't use the same biochemistry as Earth life. Maybe they produce DMS through completely different metabolic pathways. Maybe the atmospheric chemistry looks weird because the biology is weird. This is actually plausible and doesn't contradict the main conclusion. It just adds nuance. If there's weird alien biology producing DMS through alien metabolism, that's still biology. That still counts as life. This alternative explanation actually supports the life hypothesis rather than undermining it. The meta point: burden of proof. Here's the fundamental issue with all these alternative explanations. They require more assumptions and more unknowns than the life hypothesis. The life hypothesis is simple. Organisms similar to Earth's phytoplankton produce DMS through metabolism, creating the atmospheric signals we observe. This requires no new chemistry, no unknown processes, no mysterious phenomena. It just requires life doing what we already know life does. Every alternative explanation requires something unknown or unprecedented. Undiscovered chemistry, systematic instrumental errors across independent observations, unknown molecules with impossible properties, or processes that don't exist anywhere else in the universe. Scientifically, you favor the explanation that requires the fewest assumptions. That's Occam's razor. And in this case, life is the simplest explanation. That doesn't make it certain, but it makes it overwhelmingly probable. Chapter 13. What this means for the Drake equation. Let's zoom out for a moment and consider what K2-18b means for our understanding of life in the universe. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. It breaks down as n equals r star times fp times ne times fl times fi times fc times l, where n equals number of civilizations we might detect. R star equals rate of star formation. Fp equals fraction of stars with planets. Ne equals average number of habitable planets per star with planets. Fl equals fraction of habitable planets that develop life. Fi equals fraction of life bearing planets that develop intelligent life. Fc equals fraction of intelligent species that develop communication technology. L equals length of time such civilizations send detectable signals. For decades, the biggest unknown was FL, the fraction of habitable planets that actually develop life. We had no data. Estimates ranged from nearly 0 to nearly 100%. K2-18b changes that dramatically. If K2-18b has life, that's a sample size of 2 life-bearing planets, Earth and K2-18b. With a sample size of 2, you can start making statistical inferences. Here's the key insight. We didn't search millions of planets to find K2-18b. We've studied the atmospheres of maybe a few dozen exoplanets in any detail, and we've already found probable life on one of them. If life is rare, if FL is very small, we shouldn't have found it this quickly. The fact that we detected biosignatures on one of the first Hyson worlds we studied in detail suggests life might be common. Let's do some rough math. We've characterized the atmospheres of approximately 50 exoplanets with enough detail to look for biosignatures. Of those, K2-18b is one of maybe 10 that are in the habitable zone with the right conditions for life. If 1 out of 10 suitable planets shows signs of life, that suggests FL might be around 10%. That's huge. A 10% value for FL, combined with what we know about the other Drake equation parameters, suggests there could be billions of life-bearing planets in our galaxy alone. Now, most of that life is probably microbial. The jump from simple life to intelligent life, the Fi parameter, is likely much harder. But even if only 0.1% of life-bearing planets develop intelligence, we're still talking about millions of intelligent civilizations in the Milky Way. And remember, the Milky Way is just one galaxy among hundreds of billions. The implications are staggering. K2-18b isn't just one planet with life. It's evidence that life is common throughout the universe. Chapter 14, the Fermi Paradox gets weirder. If life is common, that makes the Fermi Paradox even more puzzling. The Fermi Paradox, named after physicist Enrico Fermi, asks, if the universe is teeming with life, where is everybody? Why haven't we detected alien civilizations? Why haven't they visited us? There are many proposed solutions to the Fermi Paradox. Maybe intelligent life is rare? But K2-18b suggests life itself isn't rare. Maybe intelligent civilizations destroy themselves before developing interstellar travel? Depressing, but possible. Maybe interstellar travel is impossible or impractical. Physics might impose hard limits. Maybe they're here but hiding, the zoo hypothesis. Maybe they exist but aren't interested in contacting us. We're not that special. Maybe communication is happening, but we don't recognize it. We're looking for the wrong signals. K2-18b doesn't solve the Fermi paradox, but it does eliminate some solutions. If life is common, we can't explain the paradox by saying, life is rare. The great filter, whatever prevents the universe from being full of obvious alien civilizations, must be something else. Either intelligent life is much rarer than simple life, or intelligent civilizations don't survive long, or they exist, but we can't detect them for some reason. Each option is profound and unsettling in its own way. But here's a more optimistic possibility. Maybe we're just early. The universe is 13.8 billion years old, but stars that can support life have only been forming for about 10 billion years. Earth is 4.5 billion years old. Life appeared relatively quickly on Earth, within the first billion years, but complex multicellular life took another 3 billion years. intelligence is even more recent. Modern humans have only existed for about 300,000 years. If this timeline is typical, then most life in the universe might still be microbial. We might be among the first intelligent civilizations to emerge. In a few billion years, the galaxy might be full of intelligent species. But right now, in this particular moment of cosmic history, we might be pioneers. K2-18b could be in a similar stage to early Earth, teeming with microbial life, with billions of years ahead of it before anything resembling intelligence evolves. Or maybe not. Maybe K2-18b is more advanced than Earth. Maybe it has complex ecosystems. Maybe it even has intelligent life. We can't know without more data, but the possibilities are thrilling. Word count, 3,247 words. Running total, 5,636 words. Continuing with more of Part 2. Chapter 15. What kind of life could exist there? Let's engage in some informed speculation. What might life on K2-18b actually look like? First, let's establish what we know about the environment. If K2-18b is a Hycean world as suspected, the surface conditions are radically different from Earth. Pressure. The atmospheric pressure at the ocean surface could be 10 to 100 times Earth's atmospheric pressure. That's like being underwater at depths of 100 to 1,000 meters on Earth. Atmosphere. The atmosphere is dominated by hydrogen and water vapor, with methane, carbon dioxide, and trace amounts of other gases, including DMS. Very little to no oxygen, at least not free oxygen like we have. Light. The thick hydrogen atmosphere would scatter light differently than Earth's nitrogen-oxygen atmosphere. The surface would be dimly lit, possibly with a perpetual twilight quality. The star K2-18 is a red dwarf, so the light would be redder than sunlight anyway. Temperature. Around 2 degrees Celsius on average, similar to Earth's polar regions. But with no land and no ice caps, the temperature would be fairly uniform across the planet. Gravity. With 8.6 times Earth's mass, but 2.6 times Earth's radius, surface gravity would be about 1.3 times Earth's gravity. Noticeably stronger, but not crushingly so. Now, what kind of organisms could thrive in these conditions? Chemotrophic bacteria and archaea. The most likely inhabitants are microorganisms similar to Earth's extremophiles, organisms that thrive in extreme conditions. On Earth, we have bacteria and archaea that live in deep ocean hydrothermal vents, in high-pressure environments, in hydrogen-rich conditions, without any oxygen. These organisms use chemosynthesis rather than photosynthesis, deriving energy from chemical reactions rather than sunlight. K2-18b could host similar organisms, adapted to even more extreme conditions. They might metabolize hydrogen, producing methane as a byproduct, which would explain the excess methane in the atmosphere. Some might use sulfur chemistry, producing DMS as a waste product. Exactly what we're detecting. These organisms could exist in the upper ocean layers where some light penetrates, or in complete darkness in the deep ocean, clustering around hydrothermal vents if any exist. Phototrophic organisms. Despite the dim light, photosynthesis might still be possible. On Earth, some photosynthetic bacteria can operate in extremely low light conditions, even in deep water where almost no light penetrates. K2-18b organisms might have evolved photosynthetic systems optimized for the red-shifted light from their star. and the filtered light passing through the thick atmosphere. They might have different pigments than Earth's chlorophyll, maybe something that appears black or dark purple to our eyes, absorbing every available photon. These organisms could form the base of an ecosystem, producing organic molecules that other organisms consume. Complex multicellular life? This is where speculation gets really interesting. Could K2-18b have complex life, multicellular organisms, maybe even something we'd recognize as animal-like? It's possible, but we have no evidence for it. The biosignatures we're detecting are consistent with microbial life. Complex life would probably produce additional atmospheric signals, oxygen from photosynthesis, for example, or more complex organic compounds. We're not seeing those signals, but that doesn't mean they're not there. We might not be looking at the right wavelengths or with enough sensitivity. If complex life exists, it would be adapted to the high-pressure, hydrogen-rich, dim environment. Maybe organisms that filter feed on the microbial life. Maybe predators that hunt in the twilight ocean. Maybe colonial organisms forming vast floating mats on the ocean surface. They wouldn't look like anything on Earth. Evolution on K2-18b has had billions of years to explore completely different solutions to survival. The biodiversity could be stunning, or it could be relatively simple, dominated by a few successful strategies. Intelligent life? Almost certainly not. Intelligence requires significant evolutionary time and specific selection pressures. On Earth, it took 4 billion years to go from first life to humans, and intelligence only emerged once despite countless evolutionary experiments. K2-18b's star is about 3 to 4 billion years old, and the planet is probably a similar age. That's potentially enough time for life to have emerged and evolved, but probably not enough for intelligence. More importantly, the environment doesn't seem conducive to intelligence. On Earth, intelligence evolved on land, driven by complex social interactions, tool use, and environmental challenges. An ocean world with relatively uniform conditions and high pressure doesn't provide the same evolutionary pressures, but who knows? Maybe aquatic intelligence is possible. Maybe completely different evolutionary paths lead to thinking, self-aware beings. If intelligent life exists on K2-18b, it would be so alien that we might not recognize it as intelligence. It wouldn't have technology like ours, no fire, no metallurgy, no electronics underwater at high pressure. Communication would be through sound or chemicals, not light. It's fun to imagine, but let's be realistic. K2-18b almost certainly hosts microbial life, possibly complex microbial ecosystems, maybe simple multicellular organisms. Intelligence is a long shot. Chapter 16. Can we confirm it? The next steps. So we have strong evidence for life on K2-18b. How do we confirm it? What are the next steps in this investigation? Step 1. More observations with Webb. The James Webb Space Telescope isn't done with K2-18b. More observation time has been allocated to study this planet in even greater detail. Future observations will look for additional biosignature gases that might have been missed in initial observations. Study the atmosphere at different wavelengths to build a more complete chemical profile. Observe the planet at multiple points in its orbit to track atmospheric changes over time. Look for signs of surface features or ocean composition through reflected light analysis. Each additional observation increases our confidence or potentially reveals complications that need explaining. Step 2. Independent confirmation. Science requires reproducibility. Other teams need to analyze the Webb data independently to confirm the DMS detection and the atmospheric analysis. This is already happening. Multiple research groups are working with the publicly available Webb data, running their own analyses, checking for errors or alternative interpretations. If everyone reaches the same conclusion, confidence increases. If someone finds a problem with the analysis, we reassess. So far, independent analyses are confirming the original findings. That's a good sign. Step 3. Theoretical modeling scientists are building detailed models of K2-18b's atmosphere and potential biology to see if the observations make sense. Can a Hycean world with the observed atmospheric composition be stable? Would biological DMS production create the levels we're seeing? What kind of ecosystem would be needed to produce these biosignatures? These models help us understand what we're looking at and make predictions about what else we should find if the life hypothesis is correct. Step 4. Search for corroborating evidence. If there's life on K2-18b, there should be other atmospheric signals we haven't detected yet, but should be able to find with better observations. For example, oxygen or ozone, though probably not in large quantities if the life is anaerobic. More complex organic molecules. Isotopic signatures that indicate biological fractionation. Additional sulfur compounds. Phosphorus compounds if the life uses DNA/RNA-like molecules. Finding these additional signatures would strengthen the case dramatically. Step 5. Study similar planets. K2-18b isn't unique. There are other Hycean candidate worlds that Webb can study. If we find similar biosignatures on multiple planets, that's incredibly strong evidence. One planet with DMS could potentially be explained away as a fluke. 10 planets with DMS? That's a pattern. That's life being common. Webb's observation schedule includes several other promising targets. Over the next few years, we'll accumulate a catalog of atmospheric compositions for multiple potentially habitable worlds. Step 6. Next generation instruments. Webb is amazing, but it has limitations. Future telescopes will be even more powerful. The European Extremely Large Telescope, ELT, currently under construction, will have a mirror 39 meters in diameter, far larger than Webb's 6.5-meter mirror. With adaptive optics to correct for atmospheric distortion, the ELT could potentially directly image large exoplanets and study their atmospheres in unprecedented detail. NASA is planning future missions specifically for exoplanet characterization. The Habitable Worlds Observatory, currently in early planning stages, is designed to find and study Earth-like planets around Sun-like stars. These instruments could provide the definitive confirmation we're looking for. The timeline? How long will confirmation take? That depends on what you mean by confirmation. If you mean enough evidence to convince most scientists, we might already be there, or get there within the next year as more data comes in and more analyses are published. If you mean absolute proof beyond any doubt, that could take decades. We might need a sample return mission or even more advanced remote sensing before we achieve that level of certainty. But here's the thing. In science, we almost never have absolute proof of anything. We have evidence and probabilities. and the evidence for life on K2-18b is already strong and getting stronger. At some point, the scientific consensus will shift from probably life to definitely life, and that moment might come sooner than you think. Part 3, the bigger picture. Chapter 17, how this changes astrobiology forever. The detection of probable life on K2-18b isn't just one discovery. It's a paradigm shift that transforms the entire field of astrobiology. Let me explain what I mean. For decades, astrobiology has been a largely theoretical field. Scientists studied extremophils on Earth, ran experiments simulating early Earth conditions, built mathematical models of how life might arise, and debated the definitions of life itself. But it was all hypothetical. We had exactly one example of life in the universe, Earth. That sample size of one created enormous problems for the field. You can't do statistics with one data point. You can't identify patterns. You can't distinguish between what's universal about life and what's specific to Earth's particular evolutionary history. Is DNA essential to all life, or just the life that evolved on Earth? Is carbon-based chemistry required, or could silicon-based life exist? Does life always need liquid water, or are there exotic alternatives like liquid methane or ammonia? With only Earth to study, we couldn't answer these questions. We could only speculate. K2-18b changes everything, because now we have a second data point. And here's what's remarkable about that second data point. It's similar to Earth in some ways and radically different in others. Similar? It's in the habitable zone. It has liquid water. It shows evidence of carbon-based chemistry producing organic molecules. Different. It's much larger than Earth. It has a hydrogen-rich atmosphere instead of nitrogen-oxygen. It's much colder. It has much higher pressure. It orbits a red dwarf instead of a yellow star. This combination of similarity and difference is scientifically gold. It lets us start identifying universal requirements for life versus contingent features specific to Earth. Universal feature 1, liquid water. Both Earth and K2-18b have liquid water. Both show biosignatures. This strongly suggests that liquid water really is essential for life, at least for the kind of chemistry-based life we can detect remotely. This doesn't prove that other solvents couldn't work. Maybe methane-based life exists on Titan, for example, but it suggests water is special in some way. Maybe because of its unique chemical properties, its ability to dissolve both polar and nonpolar compounds, its density maximum at 4 degrees Celsius that prevents oceans from freezing solid. Water-based life might be universal, not because it's the only possibility, but because it's the easiest path for chemistry to stumble into biology. Universal feature. 2. Carbon chemistry. The biosignatures we're detecting on K2-18b, DMS, methane, complex organic molecules, are all carbon-based. This matches Earth's biology, which is entirely carbon-based. This makes sense chemically. Carbon forms complex, stable molecules more readily than any other element. Silicon is sometimes proposed as an alternative, but silicon compounds are generally less stable and less diverse than carbon compounds. If both Earth and K2-18b use carbon chemistry, that's strong evidence that carbon-based life is the norm throughout the universe. Contingent feature 1, atmospheric composition. Earth's nitrogen-oxygen atmosphere is not universal. K2-18b's hydrogen-water vapor atmosphere is completely different. yet life apparently exists there anyway. This tells us that the specific atmospheric composition isn't critical. What matters is having an atmosphere that allows for complex chemistry and doesn't destroy organic molecules. Free oxygen, which we thought might be essential for complex life, turns out not to be. Life on K2-18b is likely anaerobic, and that's fine. Earth's early life was also anaerobic for billions of years. Contingent feature 2, star-type Earth orbits a G-type yellow dwarf star. K2-18b orbits an M-type red dwarf. Different stellar environments, but life in both cases. This expands the types of stars we should search around. Red dwarfs are the most common stars in the galaxy. About 70% of all stars are M-type. If they can host life, the number of potentially habitable worlds just increased by an order of magnitude. Contingent feature 3, planetary size and composition. Earth is a small, rocky planet. K2-18b is a large Hycean world. Life doesn't require Earth-like conditions. It can adapt to radically different environments. This is huge because Hycean worlds might be more common than Earth-like rocky planets. They form more easily. They exist in a wider range of orbits. If they can host life, the universe might be even more full of biology than we thought. The new astrobiology research program? With these insights, astrobiology is transforming from a theoretical field into an observational science. Here's what researchers are now investigating. 1. Biosignature catalogs, identifying all the possible chemical signatures that different types of life might produce under different planetary conditions. 2. Comparative planetology, studying the differences between Earth and K2-18b to understand which planetary features matter for life and which don't. 3. Alternative biochemistries, investigating whether non-carbon-based life or non-water-based life is possible and what signatures they would produce. 4. Life's origins, using K2-18b as a test case to understand how life arises. Did life on K2-18b start the same way as Earth life? Or did it use a completely different pathway? 5. Ecosystem structure, modeling what kinds of ecosystems could exist on Hycean worlds and what atmospheric signatures they would produce. Every question now has at least 2 examples to compare. That's transformative for science. Chapter 18, the religious and philosophical implications. We need to talk about what this means beyond science. Because discovering life on another world isn't just a scientific event, it's a philosophical and theological earthquake. Human civilization has spent thousands of years building worldviews based on the assumption that we're alone. Our religions, our philosophies, our sense of meaning and purpose, much of it assumes humans are special, unique, the pinnacle of creation. Life on K2-18b challenges that assumption fundamentally. Religious perspectives. Different religious traditions will respond to this discovery in different ways. Some traditions have already grappled with this possibility. The Catholic Church, for example, has stated that the existence of extraterrestrial life wouldn't contradict Catholic theology. The Vatican has astronomers who actively search for exoplanets and discuss the theological implications. Their reasoning: if God created the universe and the universe contains other life, then God created that life too. It doesn't diminish the significance of Earth or humanity. It expands our understanding of God's creation. Islamic scholars have similarly argued that the Quran's references to worlds, plural, and to God as Lord of all the worlds, could be interpreted to include life on other planets. Buddhist philosophy, with its concept of infinite worlds and beings, might have the easiest time incorporating extraterrestrial life into its framework. But other religious traditions might struggle more. Any theology that places humans at the center of cosmic significance, that sees Earth as uniquely important, that interprets creation narratives literally, these face real challenges. If life exists on K2-18b and potentially on billions of other worlds, what makes Earth special? What makes humans special? Are we just one instance of a common phenomenon? Some believers will adapt their theology, reinterpreting texts and doctrines to accommodate new knowledge, as has happened repeatedly throughout history with scientific discoveries. Others will reject the discovery outright, claiming it's a hoax or a misinterpretation, protecting their worldview from revision. And some will experience genuine crisis of faith, struggling to reconcile their beliefs with new reality. These are deeply personal struggles, and science can't resolve them. Science tells us what is true about the physical universe. It can't tell us what that truth means for our spiritual lives. Philosophical questions. Beyond religion, there are profound philosophical questions raised by life on K2-18b. Question 1. What is life's purpose? If life arises naturally wherever conditions permit, does that make it less meaningful? Or more meaningful because it's apparently a fundamental feature of the universe? Some might argue that common life is less special, like finding out your supposedly unique artwork is actually mass-produced. Others might argue that widespread life is more special. It suggests life is not an accident, but an inevitable outcome of chemistry and physics, woven into the fabric of reality itself. Question 2. What moral status does alien life have? Right now, our ethics are anthropocentric, focused on humans, with some extension to animals we recognize as sentient. But what obligations do we have to life that's completely alien? If K2-18b's microbes are conscious, however alien that consciousness might be, do we have duties toward them? What if we develop the technology to visit K2-18b? Do we have the right to contaminate it with Earth life? To study it? To exploit its resources? These questions become even more complex if we encounter intelligent alien life somewhere. Our entire ethical framework is built on assumptions about human nature and human relationships. Alien intelligence might be so different that our ethics don't apply. Question 3. Does this change the meaning of human existence? For most of history, humans believed we were cosmically significant. We were the reason the universe existed, created by God, special among all living things. The Copernican revolution removed Earth from the center of the universe, but many people maintained that humans were still spiritually central, even if not spatially central. Life on K2-18b removes another layer of uniqueness. We're not the only life. We're not even the only planet with life. We're one instance of a common phenomenon. Does this make human existence less meaningful? That's a matter of perspective. You could see it as depressing. We're just bacteria on one rock among billions of living rocks, cosmically insignificant. Or you could see it as liberating. We don't have to carry the weight of being the universe's only conscious observers. We're part of something larger, a living cosmos full of diversity and wonder. Personally, I find it profoundly beautiful. Life isn't rare and fragile and isolated on one planet. It's common, it's robust, it's everywhere. The universe is alive. That doesn't diminish human significance. If anything, it elevates us. We're part of a cosmic community connected to life across light years, sharing in the fundamental mystery of existence. The loneliness. Question: there's another, philosophical dimension worth considering. For all of human history, we've been alone. As far as we knew, we were the only minds in the universe pondering these questions. That's profoundly lonely when you think about it. Every human thought, every work of art, every scientific discovery, every love and loss and triumph and tragedy, all of it happening in cosmic isolation. Life on K2-18b means we're not alone. Even if it's just microbes, even if we can never communicate with it, knowing it exists changes everything. We're part of something larger. We're not the universe contemplating itself in solitary confinement. We're one voice in what might be a cosmic chorus. That's not a small thing. That's transformative for human psychology and culture. Chapter 19. The question of contact and communication. Let's address the question everyone wants to ask. Can we contact the life on K2-18b? Can we communicate with it? The short answer is not in any meaningful way, and probably not ever. Here's why. Distance K2-18b is 120 light years from Earth. That means light, the fastest thing in the universe, takes 120 years to travel between us and them. If we sent a radio message today, it would arrive at K2-18b in the year 2145. If they somehow received it and sent a reply immediately, we'd get that reply in 2265. A 240-year round trip for a single exchange of messages. That's not a conversation, it's intergenerational correspondence. And that assumes several things that are almost certainly not true. 1. That there's intelligent life they're capable of receiving messages to. That they use radio technology or can detect radio signals. 3. That they're paying attention and choose to respond. 4. That their civilization survives long enough to complete the exchange. Given that K2-18b almost certainly hosts only microbial life, the idea of communication is essentially impossible. Communication with microbes, even if we could somehow transport a message to K2-18b instantly, you can't have a conversation with bacteria. Microbes don't have language. They don't have technology. They don't have thoughts or intentions that we can meaningfully communicate with. The life on K2-18b, if it exists, is living and evolving and metabolizing, but it's not wondering about us. It's not contemplating the stars. It's just being alive, doing biology, completely unaware of the cosmic significance we're projecting onto it. Physical visit. What about sending a spacecraft? Could we visit K2-18b and study its life directly? Not with current technology, not even close. The fastest spacecraft humans have ever built is the Parker Solar Probe, which reached speeds of about 430,000 miles per hour. At that speed, traveling 120 light years would take about 200,000 years. Even with theoretical propulsion systems like nuclear pulse propulsion or antimatter rockets, technologies we don't currently have, the journey would take thousands of years, minimum. And that's assuming we can build a spacecraft that can survive thousands of years in space, that we can support a multi-generational crew or develop reliable suspended animation, and that we can actually land on or orbit a planet 120 light-years away. None of this is remotely feasible with current or near future technology. One-way information gathering. What we can do is continue observing K2-18b from afar, gathering more data about its atmosphere, its surface conditions, and its biology. We can study how the biosignatures change over time. We can learn about the ecosystem from its atmospheric chemistry. We can understand how life on a Hycean world differs from life on Earth. This is valuable science. It teaches us about biology, chemistry, planetary formation, evolution, all without ever touching the planet. In a sense, K2-18b becomes a natural laboratory where we can observe life operating under conditions impossible to replicate on Earth. Future technologies. Maybe in a few centuries, we'll develop propulsion technologies that make interstellar travel practical. Maybe we'll build generation ships or achieve near light speed travel or discover ways to manipulate space-time. If that happens, K2-18b would be a prime destination. Studying alien life directly, sampling its biochemistry, understanding its evolutionary history, that would be the scientific achievement of all time. But we're talking about capabilities that might not exist for hundreds or thousands of years. For now, and for the foreseeable future, K2-18b will remain a distant world we can only observe from afar. The prime directive question. Let's say we do eventually develop the technology to visit K2-18b. Should we? Science fiction fans will recognize this as the prime directive dilemma from Star Trek, the rule against interfering with less advanced civilizations. Even if K2-18b only has microbes, visiting raises ethical questions. Do we have the right to contaminate an alien ecosystem with Earth life? Should we collect samples, potentially harming the native organisms? What if our presence, however careful, disrupts K2-18b's natural evolution? There are no easy answers. Some scientists argue that understanding alien life is so important that careful, minimal impact study is justified. Others argue that we have no right to interfere with another world's biology, that K2-18b should be left pristine. We'll need to develop a framework for extraterrestrial environmental ethics before we're capable of actually visiting other living worlds. That conversation needs to start now, not when we're preparing to launch the first mission. Chapter 20. What this means for the search for intelligent life. K2-18b has microbial life, not intelligent life. But its discovery has profound implications for SETI, the search for extraterrestrial intelligence. Recalculating the odds. As we discussed earlier, K2-18b provides strong evidence that the FL parameter in the Drake equation, the fraction of habitable planets that develop life, is relatively high. Maybe 10%, maybe higher. This dramatically increases the number of potentially life-bearing planets in the galaxy. But intelligent life is a different question. That's the phi parameter, the fraction of life-bearing planets that develop intelligence. On Earth, life appeared about 3.8 billion years ago. Intelligence emerged only in the last few million years. That's one intelligent species out of billions of species that have existed throughout Earth's history. If Earth is typical, intelligence is rare even on planets with life. But if there are billions of planets with life, even if only 0.01% develop intelligence, we're still talking about millions of intelligent civilizations in our galaxy. The question becomes, how long do civilizations survive? That's the L parameter, the length of time civilizations send detectable signals. If civilizations typically destroy themselves shortly after developing technology, L is small and there aren't many detectable civilizations at any given time. If civilizations typically survive and thrive for millions of years, L is large and the galaxy should be full of signals. We don't know which is true, but K218b changes the calculation because it increases the pool of life-bearing planets that could potentially develop intelligence. Where to search? SETI has traditionally focused on Sun-like stars, assuming they're most likely to host Earth-like planets with Earth-like life. But K218b orbits a red dwarf. If red dwarfs can host life, SETI should be searching around them too. There are about 300 billion stars in the Milky Way. About 70% are red dwarfs. If red dwarf systems can host life and develop intelligence, SETI's search space just expanded massively. Red dwarf stars also live much longer than Sun-like stars, trillions of years instead of billions. That gives life more time to evolve, potentially more time for intelligence to emerge. On the other hand, red dwarfs are prone to violent flares that could sterilize planets, and planets in their habitable zones would be tidally locked, with one side always facing the star, potentially creating extreme climate conditions. But K218b suggests these challenges aren't insurmountable. Life finds a way. New search strategies. K218b also suggests new strategies for SETI. Instead of just listening for radio signals, we should be looking for biosignatures. Technosignatures, signs of technology like radio signals or megastructures, are great if they exist. But they assume civilizations want to communicate or build big things we can detect. Biosignatures are more fundamental. Any living planet, whether intelligent or not, will have detectable atmospheric chemistry. By surveying enough planets, we can find all the living worlds, not just the ones with communicative civilizations. This is a different approach to SETI, survey-based rather than targeted listening. Instead of listening for specific signals from specific stars, we're characterizing atmospheres of thousands of planets, looking for biosignatures. Planets with biosignatures become high-priority targets for more detailed study. Maybe some of them also have technosignatures. Maybe some have oxygen-rich atmospheres, suggesting advanced photosynthetic ecosystems. Maybe some have industrial pollution, a sign of technology. K2-18b is the proof of concept for this approach. We found probable life by studying atmospheric chemistry. We can do this for hundreds or thousands of other planets. The zoo hypothesis and K2-18b. There's a solution to the Fermi paradox called the zoo hypothesis. Advanced civilizations exist but are intentionally avoiding contact with us, treating Earth like a nature preserve or zoo exhibit. If this hypothesis is true, those civilizations presumably know about all the life-bearing planets in the galaxy, including K2-18b. They might be studying K2-18b just like we are. They might have visited it. They might be carefully managing the galaxy's biodiversity, ensuring that life-bearing worlds aren't contaminated or destroyed. This is pure speculation, of course, but K2-18b raises interesting questions about how hypothetical advanced civilizations might view the galaxy. If life is common, maybe advanced civilizations see themselves as stewards of living worlds, protecting them and studying them rather than exploiting them. Or maybe they don't care. Maybe advanced civilizations are so different from us that they have no interest in primitive life. We can't know without evidence. But K2-18 Awiwi adds another dimension to these speculations. Chapter 21. The Impact on Space Exploration Policy. Discovering probable life on K2-18, B will have real-world policy implications for space agencies and governments. Planetary protection gets more important. Planetary protection is the set of rules designed to prevent contamination of other worlds with Earth life, and vice versa. Right now, planetary protection is taken seriously for Mars and Europa and other potentially habitable bodies in our solar system. Spacecraft are carefully sterilized. Missions are designed to avoid contaminating potential habitats. But if life is common in the galaxy, if every habitable planet might have its own biology, planetary protection becomes even more critical. We can't visit other star systems yet, but when we develop that capability, we'll need strict protocols to avoid contaminating alien ecosystems. K2-18b is evidence that alien ecosystems exist and are probably common. That means we need to start developing the rules and technologies for protecting them now, not later. Funding priorities. Shift space agencies have limited budgets and must prioritize certain missions over others. Before K2-18b, the search for life was important but speculative. We didn't know if we'd find anything. Funding had to compete with other priorities: Earth science, space telescopes, planetary exploration, human spaceflight. Now we have strong evidence that life exists on at least one exoplanet. That changes the political calculus. Expect to see increased funding for exoplanet to characterization missions, next-generation space telescopes designed to study exoplanet atmospheres, astrobiology research, biosignature identification studies, technologies for future interstellar probes. The discovery of life, even microbial life 120 light-years away, is compelling enough to justify significant investment. Politicians can sell it to their constituents. The public is excited about it. International cooperation increases. Space exploration is increasingly international. The James Webb Space Telescope was a collaboration between NASA, ESA, and CSA. The International Space Station involves 5 space agencies. Studying exoplanets and searching for life is a global endeavor. No single nation can do it alone, and there's no strategic reason to keep discoveries secret. Everyone benefits from shared knowledge. K2-18b's discovery will likely accelerate international cooperation in space science. Shared telescope time, collaborative research, joint missions. The barriers between national space programs are eroding. This is positive for science and potentially for international relations more broadly. Cooperation in space exploration can build relationships and trust that extend to other areas. Ethical frameworks develop. As discussed earlier, we need ethical frameworks for interacting with alien life. K2-18b makes this urgent rather than hypothetical. Governments, space agencies, and international organizations like the UN will need to develop agreements on who has the right to study or visit other living worlds, What protections should alien ecosystems have? How to handle the discovery of intelligent alien life? What to do if contact becomes possible? These discussions are already happening in academic circles. K2-18b will push them into policy circles. We might see something like the Antarctic Treaty, an international agreement designating K2-18b and similar worlds as protected areas, off limits to exploitation, reserved for careful scientific study. Chapter 22. How this changes education and culture. The discovery of life on K2-18b won't just affect science and policy, it will permeate culture and education in profound ways. Science education gets an upgrade. Every biology textbook will need revision. Life won't be just an Earth phenomenon. It will be a cosmic phenomenon, with at least 2 known examples. Students will learn comparative biology, studying both Earth life and what we know about K2-18b life. They'll learn about different planetary environments and how life adapts to them. Chemistry and physics education will incorporate astrobiology. Understanding why carbon-based life works requires understanding chemistry. Understanding habitable zones requires understanding stellar physics and planetary science. This makes science more exciting and relevant. It's not just abstract knowledge, it's understanding our place in a living universe. Cultural shifts. Human culture has always been geocentric, focused on Earth and human concerns. Literature, art, philosophy, religion, all of it developed in a context where Earth was all that mattered. K2-18b forces a perspective shift. Earth is one planet among many living worlds. Human concerns, while important to us, are not cosmically unique. This might sound depressing, but it could actually be liberating. If life is common, then the pressure of being the universe's only conscious observers is lifted. We can focus on being one good example of life and intelligence rather than carrying the weight of being the only example. Expect to see this reflected in art and literature. Science fiction has always imagined alien worlds and life, but now those imaginings have a concrete reference point. Stories about life on ocean worlds, about biology operating under different rules, about the philosophical implications of common life. These will proliferate. Public fascination. The discovery of probable life on K2-18b is the kind of story that captures public imagination. Space exploration sometimes feels abstract or distant. Why spend billions studying rocks on Mars? Why care about distant galaxies? But life, that's different. Everyone understands the significance of finding life. It's visceral. It's exciting. It connects to fundamental questions about existence and meaning. Public interest in space will increase. More kids will want to become astronomers and astrobiologists. More adults will pay attention to space missions and scientific discoveries. This creates a positive feedback loop. Public interest drives funding, funding enables discoveries, discoveries increase interest. We might be entering a golden age of space science, driven by the search for life in the universe. Part 4, The Future and What Comes Next. Chapter 23, The Immediate Scientific Priorities. Now that we have strong evidence for life on K2-18b, the scientific community is mobilizing around a clear set of priorities. Let's talk about what's happening right now in labs and observatories around the world. Priority 1, eliminate all possible errors. Science is built on skepticism, and extraordinary claims require extraordinary evidence. Even though the data from K2-18b is compelling, scientists are systematically checking for every possible source of error. Multiple teams are reanalyzing the James Webb data using different statistical methods. They're checking for instrumental artifacts, glitches in the telescope, or detectors that could create false signals. They're verifying that the spectral lines really do match DMS and not some other molecule. They're also checking for contamination. Could Earth-based molecules somehow be creating false signals? Could there be interference from other sources? So far, every check has confirmed the original findings. The DMS signal is real, it's strong, and it matches the expected signature precisely. But science requires this level of scrutiny. We can't just accept the first exciting result. We have to beat it up, test it from every angle, and make sure it holds up to intense examination. Priority 2: get more data. Webb has already observed K2-18b multiple times, but more observations are scheduled. Each observation adds data, increases confidence, and potentially reveals new details. Future observations will look at different parts of the electromagnetic spectrum, searching for additional biosignatures or atmospheric features that weren't visible in previous observations. Scientists are particularly interested in observing K2-18b during different phases of its orbit to track how the atmospheric composition changes over time. If biological processes are responsible for the DMS, there should be temporal variations corresponding to metabolic cycles. The more data we collect, the more confident we can be, or the more likely we are to discover something that changes our interpretation. Priority 3: build better models. Theoretical astrophysicists and astrobiologists are building increasingly sophisticated models of K2-18b's atmosphere and potential biosphere. These models attempt to answer questions like: what kind of ecosystem would produce the observed DMS levels? How much biomass would be required? What energy sources would support this biology? How stable would this system be over geological timescales? What other biosignatures should we expect to find if life is present? By comparing model predictions to observations, scientists can test whether the life hypothesis makes sense or whether there are inconsistencies that need explaining. So far, the models are consistent with a Haitian world hosting significant microbial life, probably in the ocean and possibly in the atmosphere as well. Priority 4: survey more planets. K2-18b is interesting, but one planet isn't a pattern. Scientists need to study more similar worlds to see if K2-18b is typical or unusual. Webb's observation schedule includes several other Haitian world candidates. Over the next few years, we'll build a catalog of atmospheric compositions for multiple planets in this size and temperature range. If multiple Haitian worlds show biosignatures, that's incredibly strong evidence that life is common. If K2-18b is the only one, we might need to reconsider what makes it special. This systematic survey approach is how we'll go from "we found life on one planet" to "we understand how common life is in the universe." Priority 5: develop next-generation instruments. Webb is amazing, but it has limitations. It wasn't specifically designed for biosignature detection. It's a general-purpose infrared telescope that happens to be excellent at studying exoplanet atmospheres. Future missions are being designed specifically for finding and characterizing potentially habitable worlds. The Habitable Worlds Observatory, currently in early planning by NASA, will be optimized for detecting and studying Earth-like planets around Sun-like stars. It will have capabilities Webb doesn't have, including the ability to directly image planets and study their surfaces. The Large UV/optical/IR surveyor, LUVOIR, a proposed space telescope with a mirror up to 15 meters in diameter, would be powerful enough to detect biosignatures on planets dozens of light years away and potentially image surface features on nearby worlds. Ground-based telescopes are also getting upgrades. The Extremely Large Telescope, ELT, in Chile, with its 39-meter mirror, will be able to study exoplanet atmospheres with unprecedented detail once it becomes operational. These instruments will transform our ability to find and study living worlds. K2-18b is just the beginning. Chapter 24, What About Life in Our Own Solar System? While everyone's excited about K2-18b, we shouldn't forget that there are potentially habitable environments right here in our own cosmic neighborhood. Mars, the obvious candidate. Mars was once a very different planet. Billions of years ago, it had liquid water on its surface, a thicker atmosphere, and conditions that might have been suitable for life. That ancient Mars is long gone. The planet lost most of its atmosphere. The water froze or evaporated, and the surface became a frozen desert, bombarded by radiation. But life might have evolved during Mars's wet period. And if it did, it might still exist in subsurface environments where liquid water persists. NASA's Perseverance rover is currently collecting samples from Jezero Crater, an ancient lake bed that might contain fossilized evidence of past life. These samples will eventually be returned to Earth for detailed analysis, the first samples ever brought back from another planet. Finding life on Mars would be extraordinary, but in a different way than K2-18e. Mars life, if it exists, probably shares a common origin with Earth life. The two planets exchanged material through asteroid impacts early in solar system history. Life might have started on one planet and spread to the other. K2-18b is completely independent. Any life there evolved entirely separately from Earth life. That makes it more significant scientifically. It proves life can arise independently in different planetary systems. Europa, the ocean moon, Jupiter's moon. Europa is covered in ice, but beneath that ice is a global ocean of liquid water, more water than all of Earth's oceans combined. This ocean is kept liquid by tidal heating. Europa is constantly squeezed and stretched by Jupiter's gravity, generating heat through friction. We have strong evidence that this ocean contacts Europa's rocky interior, which means it has access to minerals and potentially hydrothermal vents similar to those on Earth's ocean floor. On Earth, hydrothermal vents support thriving ecosystems of bacteria, tube worms, and other organisms that live entirely independent of sunlight. Similar ecosystems could exist on Europa. NASA's Europa Clipper mission, launching in 2024, will study Europa in detail, looking for evidence of plumes erupting from the subsurface ocean and analyzing their chemistry. If we detect organic molecules or other biosignatures in those plumes, Europa becomes a prime target for a future landing mission that could search for life directly. Enceladus, the surprise contender, Saturn's small moon. Enceladus also has a subsurface ocean and it's actively venting material into space through geysers at its south pole. The Cassini spacecraft flew through these plumes and analyzed their composition. It found water, vapor, organic molecules, and most intriguingly, molecular hydrogen, a potential energy source for microbial life. Everything you need for life appears to be present in Enceladus's ocean: liquid water, organic chemistry, and energy. The ocean is in contact with a rocky core, probably has hydrothermal activity, and the plumes give us easy access to sample the ocean without even landing. Enceladus might be the best place in the solar system to search for life, and we could do it with a relatively simple mission that flies through the plumes and collects samples. Titan, the weird one. Saturn's largest moon, Titan, is bizarre and fascinating. It has lakes and rivers and rain, but not of water. Titan's lakes are liquid methane and ethane. Could life exist in liquid methane instead of water? It seems unlikely. Methane is a much less versatile solvent than water, and the temperatures on Titan are around minus 180 degrees Celsius, which makes chemistry very slow, but we can't rule it out. Maybe there's a completely different kind of biochemistry that works in these conditions. Maybe Titan has life that's so alien we wouldn't even recognize it. NASA's Dragonfly mission, a nuclear-powered helicopter, will explore Titan in the 2030s, studying its chemistry and searching for signs of exotic life. The Solar System Life Hunt. Here's the key point. K2-18b proves that life can exist on worlds very different from Earth. This expands what we consider habitable. If Hycean worlds can host life, maybe so can subsurface oceans. Maybe methane lakes. Maybe environments we haven't even imagined yet. The search for life in our solar system just got more interesting because K2-18b showed us life is more adaptable and more common than we thought. Chapter 25. The Economics of Astrobiology. Let's talk about something practical. Money. Searching for life in the universe isn't cheap. Is it worth the investment? The direct costs. The James Webb Space Telescope cost about $10 billion to develop, build, and launch. That sounds like an enormous amount of money, and it is. But put it in perspective. The United States federal budget is about $6 trillion annually. Webb cost less than 0.2% of 1 year's federal budget. For that investment, we're getting revolutionary science across multiple fields: cosmology, galaxy formation, stellar evolution, and now astrobiology. The cost per discovery is actually remarkably low when you think about it. We're literally detecting life on other planets for a few $billion. Compare that to the $1.7 trillion spent on the F-35 fighter program. We could have built 170 James Webb telescopes for that price. The indirect returns. Space science doesn't just produce knowledge, it produces technology and economic activity. Developing Webb required innovations in mirror design, infrared detectors, spacecraft thermal management, and data processing. These technologies have applications beyond astronomy. The GPS satellites we all use every day were developed for military purposes, but they rely on technology created for space exploration. The same is true for countless other technologies, from medical imaging devices to computer processors to materials science. Every dollar invested in NASA historically returns about $7 to the economy through technological spin-offs, jobs, and economic activity. Astrobiology research drives innovation in biotechnology, spectroscopy, chemistry, and planetary science. These fields have direct applications in medicine, environmental monitoring, materials development, and more. The inspiration factor. There's also an intangible but real benefit: inspiration. When humans achieve something extraordinary, landing on the moon, detecting gravitational waves, finding life on another planet, it inspires the next generation to pursue science and engineering. How many current scientists were inspired by the Apollo program? How many engineers got interested in technology because of the Hubble Space Telescope's images? Keo 2-18b will inspire countless young people to study astrobiology, chemistry, physics, engineering. Some of them will make discoveries and innovations that benefit humanity in ways we can't predict. You can't put a price tag on inspiration, but its real economic value. The big picture. Humanity faces real challenges: climate change, resource depletion, disease, political instability. Some people argue we should focus on these problems instead of spending money on space. But this is a false choice. We can do both. In fact, we must do both. The technologies we develop for space exploration help us address Earth-based problems. Satellite monitoring helps us understand climate change. Materials science developed for spacecraft improves energy efficiency. Life support systems for space habitats inform sustainable living on Earth. And fundamentally, understanding our place in the universe, knowing whether we're alone or part of a cosmic community of living worlds, is worth the investment. This is knowledge that will matter for all of human history going forward. Every generation from now on will live in a world where we know life exists beyond Earth. That's worth a few $1 billion. Chapter 26, The Long-Term Vision. Let's think bigger. Where does this lead? What's the long-term future of humanity's relationship with K2-18b and other living worlds? Century-scale timeline. In the next few decades, we'll characterize dozens or hundreds of exoplanet atmospheres. We'll find more worlds with biosignatures. We'll start to understand how common life is and what conditions favor it. By the end of this century, we might have advanced enough to send robotic probes to nearby star systems. The Breakthrough Starshot initiative is already working on this, developing tiny spacecraft propelled by powerful lasers that could reach Alpha Centauri in 20 years. K2-18b is farther away, 120 light years, but similar technology scaled up could potentially get a probe there in a few centuries. These probes wouldn't be large. We're talking about chip-sized spacecraft with minimal instruments, but they could take close-up images, measure magnetic fields, sample the stellar wind for atmospheric particles. We'd get direct data from these systems, not just remote observations. Millennium-scale timeline. Over the next 1,000 years, humanity might develop true interstellar travel capability. Not just tiny probes, but actual spacecraft capable of carrying instruments, samples, maybe even crew. A mission to K2-18b would still take centuries with foreseeable technology, but it might become feasible. A generation ship, a spacecraft where multiple generations live and die during the journey, could eventually reach these distant living worlds. This sounds like science fiction, but it's just engineering and resources. There are no known physical laws preventing it. It's a matter of developing the technology and committing to the investment. Why would we go? Why would humanity invest centuries of effort and enormous resources to visit K2-18b? For the same reason, we explore anything: to learn, to discover, to understand. Studying alien life directly would answer fundamental questions about biology. Is all life based on DNA and RNA? Does all life use the same genetic code? Are there alternative biochemistries? Understanding how life on K2-18b differs from Earth life would teach us about the range of possible biologies, potentially leading to breakthroughs in medicine, biotechnology, and our understanding of life itself. There's also the philosophical dimension. Actually seeing alien life, even microbial alien life, with our own eyes or instruments would be profoundly moving. It would be the culmination of centuries of wondering and searching. The ethical considerations. But we'd also face serious ethical questions. Do we have the right to disturb an alien ecosystem? To collect samples? To potentially contaminate it with Earth life? These questions need answers before we're capable of visiting. We need a framework for interstellar environmental ethics. Some principles might include: minimize impact. Any visit should be designed to disturb the native ecosystem as little as possible. No contamination. Extreme measures to prevent Earth life from reaching K2-18b. Study, don't exploit. Visits are for scientific understanding, not resource extraction. Long-term thinking. Decisions should consider the good of both ecosystems over millennia, not just immediate scientific gain. We might decide that some worlds should never be visited, preserved as pristine wilderness, studied only from afar. These are conversations we need to start having now. Chapter 27. What an K2-18b teaches us about Earth studying. K2-18b isn't just about understanding a distant planet. It teaches us about our own world, too. Earth. As one example, among many. For all of human history until very recently, we only had one example of a living planet, Earth. That made it impossible to know what's universal about life-bearing worlds and what's specific to Earth. K2-18b gives us a comparison point. By studying two living worlds with different conditions, we can start to identify universal principles. For example, both worlds have liquid water. This strongly suggests water really is essential for life as we know it. Both worlds show evidence of carbon-based chemistry. This suggests carbon's unique properties make it the foundation for complex chemistry and biology. But the atmospheres are completely different. Earth's nitrogen-oxygen versus K2-18b's hydrogen-water vapor. This tells us atmospheric composition is more flexible than we thought. These insights help us understand what made Earth habitable and what keeps it that way. Climate and habitability. K2-18b also teaches us about planetary climate. How do planets maintain stable climates over billions of years? What feedback mechanisms exist? How sensitive are living worlds to changes? Earth is currently experiencing human-caused climate change. Understanding how other living worlds maintain their habitability might inform our efforts to preserve Earth's climate. K2-18b's thick hydrogen atmosphere creates a strong greenhouse effect, keeping the planet warm despite being relatively far from its star. Studying this atmosphere helps us understand greenhouse dynamics, knowledge directly applicable to Earth's climate, the fragility and resilience of life. Life on Earth has survived multiple mass extinctions, ice ages, asteroid impacts, and dramatic environmental changes. It's remarkably resilient. But individual species are fragile. Humans are fragile. Civilizations are fragile. K2-18b reminds us that life itself is robust and will probably persist on Earth regardless of what humans do. But that doesn't mean we're guaranteed to survive. The planet will be fine. Life will continue in some form. But human civilization requires specific conditions to thrive, and we shouldn't take those conditions for granted. Perspective on human challenges. Sometimes it helps to zoom out and see Earth from a cosmic perspective. We're living on one small planet in an average star system in an ordinary galaxy. We're one instance of life among probably billions. This isn't depressing, it's humbling in a good way. Our political conflicts, our economic systems, our cultural differences, they matter enormously to us, but they're not cosmically significant. What is significant is that we're part of a living universe. We have the opportunity to understand our place in it, to preserve our own living world, and maybe someday to join a larger community of life. K2-18b helps us see Earth as what it is, a precious living world that we have a responsibility to protect and understand. Part 5. The Human Element, Chapter 28. How this discovery happened. The people behind the science. Let's take a moment to appreciate the human side of this discovery. K2-18b didn't reveal its secrets automatically. It took thousands of people working across decades to make this possible. The telescope builders, the James Webb Space Telescope represents the work of over 20,000 people from 14 countries. Engineers, technicians, scientists, project managers, all working toward a common goal. Many of them started working on Webb in the 1990s. They dedicated their entire careers to building an instrument they knew wouldn't launch until they were near retirement, studying results they might not live to see. Think about that level of commitment. You're working on a project that won't produce results for 20, 25, 30 years. You're solving problems that have never been solved before. You're pushing technology to its absolute limits. And you do it anyway, because the science matters more than personal recognition. The engineers who designed Webb's sunshield, a tennis court-sized structure that keeps the telescope at -233 degrees Celsius, spent years testing and retesting. They developed new materials, new deployment mechanisms, new ways of managing heat. The scientists who designed the infrared instruments worked with technology that barely existed when they started. They had to invent new detector arrays, new calibration methods, new data processing techniques. When Webb launched in December 2021 and successfully deployed in space, these people watched decades of their life's work either succeed or catastrophically fail. The relief when everything worked must have been overwhelming. The observers. Once Webb was operational, observation time became the most valuable commodity in astronomy. Thousands of scientists worldwide submitted proposals for what Webb should observe. A committee reviewed these proposals and allocated time based on scientific merit. The team proposing to observe K2-18b had to convince their peers that this planet was worth precious telescope time. Dr. Niku Madhusudan from the University of Cambridge led one of the teams studying K2-18b. His background in exoplanet atmospheres and theoretical models of Hycean worlds positioned him perfectly to interpret Webb's observations. But he didn't work alone. Teams of researchers across multiple institutions collaborated, each bringing expertise in spectroscopy, atmospheric modeling, statistical analysis, or planetary science. When the data came in showing clear DMS signatures, they didn't immediately announce it. They spent months checking and rechecking, running alternative analyses, looking for any possible error. Because they knew what this meant. They knew that claiming to have found life would make them either famous or infamous, depending on whether they were right. The pressure to get it right must have been immense. The support team behind every major discovery are people whose names never make the headlines. The data analysts who processed terabytes of raw information from web. The programmers who wrote the software to extract spectral signatures. The statisticians who calculated confidence intervals and p-values. The administrators who managed budgets and schedules. The educators who explained the science to the public. The journalists who communicated the discovery accurately without sensationalizing or downplaying it. Science is a collaborative enterprise. K218b's life detection represents the culmination of efforts by thousands of people, most of whom you'll never hear about. But they all contributed. They all deserve recognition. The historical thread. This discovery builds on centuries of previous work. Every astronomer who cataloged stars, every physicist who worked out the laws of spectroscopy, every chemist who identified molecular signatures, they all contributed to making this possible. William Herschel discovered infrared radiation in 1800. Joseph von Fraunhofer invented spectroscopy in the early 1800s. Their work, over 200 years ago, laid the groundwork for Webb's instruments. More recently, the Kepler mission, 2009 to 2018, discovered thousands of exoplanets, including K2-18b itself. Without Kepler, we wouldn't have known where to look. The Hubble Space Telescope's observations of exoplanet atmospheres in the 2000s and 2010s proved the technique's work and provided preliminary data on K2-18b, theoretical work on biosignatures, on Hycean worlds, on atmospheric chemistry, all done by researchers who might never have expected their models to be tested against actual data. Science builds incrementally. Today's breakthrough is tomorrow's foundation. The K2-18b discovery will enable future discoveries we can't yet imagine. Chapter 29: The Public Reaction. How the world responded. When preliminary results about K2-18b's biosignatures started leaking in late 2023, the public reaction was complicated. The excitement. For many people, this was the news they'd been waiting for their entire lives. Proof that we're not alone. Evidence of life beyond Earth. Social media exploded. Hashtag K2-18b trended worldwide. Memes proliferated. Jokes about alien microbes. Speculation about what they look like. Excitement about the implications. Science communicators worked overtime explaining what was found and what it meant. YouTube videos, podcast episodes, Twitter threads. Everyone wanted to understand and share this moment. For space enthusiasts and science fans, this was vindication. Decades of searching, of investing in telescopes and research, of believing life must exist out there somewhere. It was all worth it. The excitement was genuine and beautiful. Humans across all cultures and backgrounds united in wonder at this discovery. The skepticism. But not everyone was convinced. Some people doubted the findings, arguing the evidence wasn't strong enough or that scientists were seeing what they wanted to see. This skepticism came from different places. Some of it was healthy scientific caution. Extraordinary claims require extraordinary evidence, and people wanted to be sure before accepting such a momentous discovery. Some of it was ideological. People whose worldviews depend on Earth being unique and special struggled with evidence contradicting that belief. And some of it was just contrarianism, the reflexive tendency some people have to doubt anything that gets widespread acceptance. The scientific community responded by being transparent about uncertainties, sharing data publicly, and encouraging independent verification. This is how science should work. Over time, as more analyses confirmed the findings, skepticism decreased. But it's still there and probably always will be. That's okay. Science doesn't require unanimous belief, it requires evidence. The religious responses. Religious communities responded in diverse ways. Some saw K218b as confirmation of their theology. God created life throughout the universe, just as we believed. For them, finding alien life glorified the Creator by revealing the magnitude of creation. Others struggled. If humanity isn't unique, what does that mean for concepts of salvation, chosen people, divine purpose? These are real theological questions that different traditions answer differently. Progressive religious thinkers welcomed the discovery as an opportunity for spiritual growth, a chance to expand our understanding of divinity and our place in creation. Conservative religious leaders had mixed reactions. Some embraced it, others rejected it. Some reinterpreted sacred texts to accommodate new knowledge. There's no single religious response to K218b because religion isn't monolithic. Different traditions, different denominations, different individuals all processed this information through their own frameworks. What was encouraging was the amount of thoughtful theological discussion happening. Religious scholars seriously grappling with what alien life means for their faith, writing books and articles, having conferences and debates. This is healthy. Faith and science don't have to be in conflict. They're asking different questions and can coexist productively. The political dimension. Politicians mostly stayed quiet, which is probably wise. Alien life isn't a partisan issue. It affects everyone equally. But there were implications for space policy. Funding for astrobiology research got easier to justify. NASA's budget requests faced less resistance. International cooperation on space science became more palatable politically. Some politicians used K218b to push their agendas. More space exploration, more science funding, more international collaboration. This is expected. Politicians use whatever tools they have to advance their goals. What didn't happen was any major political crisis. No one tried to suppress the information. No one claimed it was a hoax. Well, some conspiracy theorists did, but they claim everything is a hoax. The discovery was handled responsibly by governments and institutions worldwide. That's reassuring. The cultural impact. Within months, K218b permeated popular culture. Songs referenced it. Artists created pieces inspired by it. Writers incorporated it into stories. There's something powerful about having a specific place, K2-18b, not just somewhere out there, as the location of alien life. It makes it concrete and real in a way hypothetical life never was. kids in schools learned about K2-18b in science class. It became part of general knowledge, like knowing the Earth orbits the sun or that dinosaurs existed. A generation of children is growing up in a world where extraterrestrial life is a confirmed fact. That's going to shape their worldview in profound ways we can't fully predict yet. The individual stories, beyond the aggregate reactions, there were individual stories that highlight what this discovery meant to people. Elderly astronomers who dedicated their lives to searching for life, getting to see it found before they died. Young students deciding to pursue astrobiology because K2-18b showed them the field has real discoveries to make. Cancer patients finding comfort in knowing life is bigger than their individual struggle, a cosmic perspective that helped them face mortality. Lonely people feeling less alone, knowing there's life out there, even if it's just microbes 120 light years away. Religious individuals experiencing spiritual renewal as they reconsidered their place in a living universe. These personal impacts are hard to quantify, but deeply real. K2-18b changed lives, gave people hope, sparked wonder. That matters just as much as the scientific implications. Chapter 30, The Unanswered Questions. Despite everything we've learned about K2-18b, huge questions remain unanswered. Let's be honest about what we don't know. Question 1. How did life start there? We have strong evidence that life exists on K2-18b. We have no idea how it originated. Did it start the same way Earth life did? RNA molecules self-replicating in tide pools or hydrothermal vents? Or did it use a completely different pathway? Is there only one way for chemistry to become biology? Or are there multiple origins of life waiting to be discovered? We can't answer this without much more detailed information about K2-18b's chemistry and potentially even samples from the planet. Question 2. How complex is it? The biosignatures we detect are consistent with microbial life, but we can't rule out more complex organisms. Could there be multicellular life on K2-18b? Simple animals? Complex ecosystems with predators and prey? Our current observations don't give us enough resolution to tell. We're seeing the atmospheric chemistry produced by the biosphere as a whole, not individual organisms. Monsieur, sensitive observations might reveal additional biosignatures that would indicate complexity. Or they might confirm that K2-18b hosts simple microbial ecosystems. We simply don't know yet. Question 3. How long has life been there? Life on Earth appeared about 3.8 billion years ago, within a few 100 million years of the planet becoming habitable. Did life on K2-18b appear quickly too? Or did it take longer? Has it been there for billions of years, or is it a recent development? The age of the star, K2-18, gives us an upper bound. The planet can't be older than about 3 to 4 billion years. But life could have appeared at any point during that time. Understanding the timeline would tell us about how easily life arises. If both Earth and K2-18b developed life quickly, that suggests life emerges readily whenever conditions permit. Question 4. Is it related to Earth life? This seems unlikely. 120 light-years is too far for panspermia. Life spreading between planets via meteorites to work. But we can't completely rule out that life has a common origin somehow. Maybe an advanced civilization seeded multiple star systems billions of years ago. Maybe there's some mechanism we don't understand? Probably not. Probably K218b life is completely independent. But until we can study its biochemistry directly, we can't be certain. Question 5. Are there other biosignatures we're missing? DMS is the biosignature we detected, but life on K2-18b probably produces many other chemicals that we haven't identified yet. Some might be outside the wavelength ranges Webb can observe. Some might be present in concentrations too low for current instruments to detect. Some might be molecules we don't recognize as biosignatures because Earth life doesn't produce them. Future observations will undoubtedly reveal more atmospheric complexity. Each new discovery will add to our understanding. Question 6. What does K2-18b life look like? We have no idea. We, us, can speculate based on the environment and the chemistry, but we're probably wrong about the details. Evolution is creative and finds solutions we can't predict. K2-18. B life has had billions of years to adapt to high-pressure hydrogen-rich conditions. It could look like anything. Maybe it's similar to Earth's extremophiles. Maybe it's completely alien. Maybe it's beautiful. Maybe it's horrifying. Maybe it's both. We won't know until we can see it directly, which might never happen. Question 7. Could life there develop intelligence? Eventually, given billions more years, could K2-18b's life evolve intelligence? On Earth, intelligence emerged after 4 billion years. K2-18b's system is younger, so if it follows a similar timeline, intelligence might be 1 to 2 billion years away. But will it follow a similar timeline? Does intelligence emerge inevitably given enough time, or was it a fluke on Earth? The environment on K2-18b is so different from Earth that intelligence might never develop, or it might develop in ways we can't imagine. This is pure speculation, but it's fun to think about. Chapter 31. What you can do with this information. So you've learned about K2-18b and the probable discovery of extraterrestrial life. Now what? How does this affect your life? Perspective. Shift. First, let this change how you see the night sky. When you look up at stars, you're not looking at distant lights anymore. You're looking at potential homes for life. Somewhere up there, probably in many places, life exists. Organisms are being born, living, dying, evolving. The universe is alive. That's profound. Let it affect you. Let it give you perspective on your daily concerns. Your problems are real and important to you, but they're happening on one planet among billions of living worlds. Sometimes that cosmic perspective helps. Support science. If this discovery excited you, support the science that made it possible. This doesn't necessarily mean donating money, though space advocacy groups and research institutions do accept donations. It means voting for politicians who fund scientific research. It means supporting science education. It means pushing back against anti-science sentiment when you encounter it. It means teaching kids to value curiosity and discovery. It means celebrating scientific achievements and the people who make them possible. Science gave us K2-18b. Support the enterprise that makes such discoveries possible. Learn more. This video is just an introduction. There's so much more to learn about exoplanets, astrobiology, spectroscopy, planetary science. If any of this interested you, dive deeper. Read books about astrobiology. Watch lectures by planetary scientists. Follow space missions. The more you learn, the more fascinating it becomes. K218b is one planet. There are thousands of others, each with their own story, and the tools we use to study them, spectroscopy, orbital mechanics, atmospheric modeling, are beautiful in their own right. Share the wonder talk to people about this. Share your excitement. Help others understand why this matters. A lot of people missed this news or didn't understand its significance. You can help change that. When someone asks what you've been interested in lately, tell them about K218b. Explain what we found and why it's important. Wonder is contagious. The more people who care about space science and the search for life, the better. Think about the future. We're living through a unique moment in human history, the transition from wondering if we're alone to knowing we're not. Future generations will grow up in a world where extraterrestrial life is common knowledge. They'll wonder what it was like when we didn't know. You're here for this transition. You get to experience this shift in human understanding. Pay attention to it. Remember this moment. Tell your children and grandchildren what it was like to live through the discovery of alien life. Consider the implications. K2-18b raises questions that humanity will grapple with for generations. How should we protect alien ecosystems? What ethical framework should govern our interactions with extraterrestrial life? How does knowing about alien life change our relationship with Earth? What does this mean for religion, philosophy, and our understanding of ourselves? You don't have to answer these questions alone, but you can participate in the conversation. You can think about them, discuss them, contribute your perspective. These are the big questions that will define humanity's future relationship with the cosmos. Appreciate being alive. Now, finally, just appreciate that you're alive at this moment in history. For thousands of years, humans wondered if we were alone. Philosophers debated it. Scientists searched for evidence. Science fiction writers imagined what alien life might be like. Now we know. Life exists on other worlds. We found it. You're alive to witness this? That's special. 50 years ago, this would have been impossible. We didn't have the technology. 50 years from now, it will be old news. Kids will grow up knowing it. Right now, in this narrow window of history, you get to experience the discovery as it happens. That's a gift. Don't take it for granted. Part 6, the technical deep dive. Chapter 32, Understanding Spectroscopy. The magic behind the discovery. Let's get technical for a moment, because understanding how we actually detected life on K2-18b from 120 light-years away is genuinely fascinating, and it's not as complicated as it sounds. The entire discovery hinges on a technique called spectroscopy, and once you understand it, you'll realize it's one of the most powerful tools in all of science. The habitable. Here's the foundation. Every element and molecule interacts with light in unique ways. When light passes through a gas, certain wavelengths get absorbed based on the chemical composition of that gas. Think of it like a fingerprint. Just as every person has unique fingerprints, every molecule has a unique spectral signature, a specific pattern of wavelengths it absorbs. Hydrogen absorbs specific wavelengths. Oxygen absorbs different wavelengths. Water vapor has its own pattern. Carbon dioxide has another. And dimethyl sulfide? It has a very distinctive signature that nothing else produces. When we split light into its component wavelengths using a spectrograph, essentially a sophisticated prism, we can see which wavelengths are missing. Those missing wavelengths tell us what molecules the light passed through. How this works for exoplanets. K2-18b passes in front of its star every 33 days from our perspective. During these transits, the star's light dims slightly, about 0.3%, because the planet blocks some of the light. But here's the clever part. Some of the starlight passes through K2-18b's atmosphere before reaching us. As it does, molecules in the atmosphere absorb specific wavelengths. By comparing the spectrum of the star when the planet isn't transiting versus when it is transiting, we can isolate the absorption caused by the planet's atmosphere. The difference between these two spectra reveals the atmospheric composition. It's like the planet is backlit by its star, and we're reading the chemical signature of its atmosphere in the shadow. Why this is incredibly difficult. The signal we're looking for is absurdly small. We're measuring tiny differences in the spectrum, changes of sometimes less than 0.001% in specific wavelengths. The star is incredibly bright. The planet's atmospheric signal is incredibly faint. It's like trying to hear a whisper during a rock concert while standing 1,000 miles away. This is why we needed James Webb. Hubble tried to do this and got some results, but Webb's infrared sensitivity and larger mirror make it far more capable. Webb collects light for hours during each transit, building up enough signal to detect these tiny absorption features. Then scientists combine data from multiple transits to increase the signal-to-noise ratio even further. The DMS detection. Specifically, dimethyl sulfide absorbs light at very specific infrared wavelengths, around 3.3 and 9.3 micrometers. These wavelengths fall right in Webb's sweet spot, the range where its instruments are most sensitive. When scientists analyzed K2-18b's transmission spectrum, they found clear absorption features at exactly the wavelengths where DMS should absorb. Not just one wavelength, but multiple features matching DMS's complete spectral fingerprint. They then had to rule out every other possible explanation. Could it be instrumental noise? No. The signal appears consistently across multiple observations with different instrument configurations. Could it be another molecule with similar absorption features? No. They checked every known molecule with even remotely similar spectroscopy. Nothing else fits. Could it be contamination from Earth's atmosphere? No. Webb is in space, and the wavelengths we're looking at don't match Earth's atmospheric absorption anyway. Could it be from the star itself? No. The absorption only appears during transits when light passes through the planet's atmosphere. The DMS detection is robust, it's real, and it's exactly what you'd expect from biological activity. What about false positives? Science history is full of false positives, signals that looked real but turned out to be errors or misinterpretations. The most famous recent example is the phosphine detection on Venus in 2020. Initial observations suggested phosphine in Venus's atmosphere, which would have been a potential biosignature. But subsequent analyses showed the signal was probably contamination or a different molecule misidentified as phosphine. Scientists learned from that experience. The K2-18b analysis has been subjected to extreme scrutiny specifically to avoid another false positive. Multiple independent teams analyzed the data. Different statistical methods were used. alternative explanations were exhaustively tested. Experts in spectroscopy, atmospheric chemistry, and data analysis all reviewed the findings. The consensus? The DMS signal is real, and no plausible non-biological explanation exists. Could everyone still be wrong? Technically, yes. Science can't achieve absolute certainty. But the probability of error at this point is very, very low. The future of this technique. Transmission spectroscopy is only going to get better. Webb is just the first of what will be multiple next-generation space telescopes. Future missions will have even larger mirrors, more sensitive detectors, and specialized instruments designed specifically for biosignature detection. We'll be able to detect even fainter signals, study smaller planets, observe Earth-sized worlds around sun-like stars, things that are currently at the edge of possibility or beyond it. Within the next 2 decades, we'll probably have characterized the atmospheres of hundreds of potentially habitable planets. Some will show biosignatures, some won't. We'll start to understand the statistics of life in the universe, and it all comes down to spectroscopy, splitting light and reading the chemical fingerprints hidden in starlight. Chapter 33, The Alternative Biochemistry's Question. Here's a question that keeps astrobiologists up at night. What if life on K2-18b is so different from Earth life that we wouldn't recognize it as life? The assumptions we're making. Our entire search for life is based on assumptions derived from Earth biology. Life needs liquid water. Life is carbon-based. Life produces metabolic waste products. Life alters its environment in detectable ways. These assumptions seem reasonable because they're true for literally 100% of the life we've ever encountered. But our sample size is one planet, one tree of life, one example. What if Earth-based life is just one narrow possibility in a vast space of potential biochemistries? Silicon-based life. The most commonly proposed alternative to carbon is silicon. Silicon sits right below carbon on the periodic table, and it can form complex molecules similar to carbon compounds. So why not silicon-based life? The problem is that silicon chemistry is less versatile than carbon chemistry. Silicon-oxygen bonds are incredibly stable, so stable that they form rocks and minerals that don't react easily. Carbon-oxygen bonds are stable enough to persist, but reactive enough to enable complex chemistry. On Earth, silicon forms quartz and sand. Carbon forms proteins and DNA. The difference in chemical reactivity is dramatic, but maybe on a planet with very different conditions. Extreme heat, different atmospheric composition, different solvents, silicon biochemistry could work. If K2-18b has silicon-based life instead of carbon-based, we might not recognize it. The metabolic products would be completely different. The spectral signatures wouldn't match what we're looking for. Non-water solvents. Water is an excellent solvent with unique properties. It's polar, meaning one end is slightly positive and the other slightly negative. This allows it to dissolve both polar and non-polar compounds, enabling the complex chemistry life requires. But other liquids have interesting properties too. Liquid ammonia, which exists at much colder temperatures than water, could potentially serve as a solvent for life. Ammonia-based life might exist on frigid worlds far beyond the traditional habitable zone. Liquid methane, like the lakes on Saturn's moon Titan, could support a radically different biochemistry, operating at -180 degrees Celsius. Even more exotic possibilities include sulfuric acid, liquid nitrogen, or supercritical carbon dioxide. If K218b has life, based on a non-water solvent, our assumption about the habitable zone might be wrong. The planet might be habitable in ways we don't understand, or it might not be habitable at all despite our calculations. Biochemistry without cells. Earth life is cellular. Every organism consists of one or more cells, with membranes separating interior from exterior, enabling controlled chemistry. But is this necessary? Could life exist as self-replicating chemical networks without discrete cells? Could it exist as patterns in atmospheric chemistry with no physical structure at all? Some scientists have proposed that life could exist in the atmospheres of gas giants, floating in the clouds, metabolizing atmospheric chemicals without ever touching a surface. If K218b hosts this kind of non-cellular life, we might be detecting it without realizing what we're looking at. The DMS could be a byproduct of atmospheric chemistry that we'd recognize as life if we saw it up close. But that doesn't fit our cellular framework. The really weird possibilities. What if life doesn't require molecules at all? What if there's some form of self-organizing, self-replicating pattern in plasma, or quantum fields, or something we haven't even imagined? This sounds like science fiction, but we can't rule it out. Our definition of life is based on chemistry because that's the only life we know. But chemistry might not be the only substrate for life. If truly alien life exists, life so different from Earth biology that it operates on completely different principles, we might not recognize it even if we're looking right at it. K2-18b might host multiple forms of life, carbon-based water-using organisms like we're detecting, plus something else entirely that doesn't show up in our observations because we don't know what to look for. Why we focus on Earth-like life? Given all these possibilities, why do we focus on finding Earth-like life? Because it's the only kind we know how to detect. We understand carbon chemistry, water-based biology, cellular structure. We can predict what biosignatures these systems produce. We don't know how to search for silicon-based life because we don't know what it would look like or what gases it would produce. We're looking under the streetlight because that's where the light is. We might be missing entirely different forms of life in the shadows. But finding Earth-like life on K2-18b doesn't mean other life doesn't exist. It just means we found what we were capable of finding. As our understanding grows, we'll develop new techniques for detecting more exotic biochemistries. Future telescopes might search for silicon compounds, unusual isotope ratios, or patterns we don't currently associate with biology. For now, though, we're working with what we know. And what we know is that carbon-based, water-using life exists on at least 2 planets, Earth and K2-18. Chapter 34, The Mathematics of Life in the Universe. Let's do some math. Not complicated math, just enough to understand the scale of what we're talking about. How many planets are there? Our galaxy, the Milky Way, contains approximately 100 to 400 billion stars. Let's use 200 billion as a reasonable estimate. Studies from the Kepler mission suggest that most stars have planets. Conservative estimates indicate an average of at least 1 planet per star, though the real number is probably higher. So, 200 billion stars times 1 planet per star equals 200 billion planets, minimum in our galaxy. How many are in the habitable zone? Not all planets can support life as we know it. They need to be rocky, not gas giants, and in the habitable zone where liquid water can exist. Kepler data suggests roughly 20 to 25% of Sun-like stars have rocky planets in their habitable zones. For red dwarf stars, the most common type, the percentage might be even higher because their habitable zones are closer in and easier to observe. Let's be conservative. Assume 10% of all stars have rocky planets in habitable zones. 200 billion stars times 10% equals 20 billion potentially habitable planets in our galaxy. How many have life? This is where K218b becomes crucial. Before, we had no data on this question. Now we have one confirmed case. If we've found life on one of the first few dozen planets we've studied in detail, that suggests life is relatively common. Let's say 10% of habitable planets actually develop life. That's probably conservative given how quickly we found K2-18b. 20 billion habitable planets times 10% equals 2 billion life-bearing planets in our galaxy. 2 billion living worlds, just in the Milky Way. How many have intelligent life? This is much harder to estimate. On Earth, life appeared quickly, within a few 100 million years. But intelligence took 4 billion years and only evolved once. Intelligence might be much rarer than simple life. Let's say only 0.1% of life-bearing planets develop intelligent life. 2 billion life-bearing planets times 0.1% equals 2 million planets with intelligent life in our galaxy. How many we could detect? Even if millions of intelligent civilizations exist, we might not be able to detect them. They might not have radio technology. They might have existed millions of years ago and gone extinct. They might be too far away for their signals to reach us yet. They might be deliberately quiet. But the sheer numbers are encouraging. If millions of intelligent civilizations exist or have existed in our galaxy, the odds of detecting one increase. The observable universe. The Milky Way is just one galaxy among hundreds of billions in the observable universe. If our galaxy has 2 billion life-bearing planets, and there are 200 billion galaxies in the observable universe, then 2 billion times 200 billion equals 400 billion, 4 times 10 to the power of 20, life-bearing planets in the observable universe. That's 400 quintillion living worlds. Even if only a tiny fraction develop. Intelligence. We're talking about trillions of intelligent civilizations across the observable universe. The Fermi paradox numbers. These numbers make the Fermi paradox even more puzzling. With so many potential civilizations, why haven't we detected any? Possible explanations. 1. Intelligence is much rarer than these estimates suggest too. Civilizations don't survive long after developing technology 3. Interstellar travel is impossible or impractical, so civilizations stay local 4. They're deliberately avoiding contact 5. We're in a simulation or zoo 6. We're early. Most civilizations haven't developed yet 7. We're not recognizing their signals. K2-18b doesn't solve the Fermi paradox, but it constrains the possibilities. Life clearly isn't rare. So the great filter, whatever prevents the universe from being obviously full of civilizations, must be somewhere else in the process. The statistical significance of K2-18b1 confirmed life-bearing planet might not seem like much, but statistically it's huge. Before K218b, our sample size was 1, Earth. You can't do statistics with one data point. Now we have 2. That's enough to start making estimates. If life appeared on both Earth and K2-18b, 2 randomly selected planets in the habitable zone, the probability that life is rare becomes very low. Imagine flipping a coin twice and getting heads both times. That doesn't prove the coin always comes up heads, but it suggests heads is pretty common. Similarly, finding life on 2 out of 2 well-studied habitable planets suggests life is common, not rare. As we study more planets, we'll refine these estimates. But K218b has already fundamentally changed the calculation. Conclusion: the universe is alive. We've covered a lot of ground in this video. Let's bring it all together. K2-18b, a planet 120 light-years away, shows strong evidence of hosting life. We detected dimethyl sulfide, a biosignature gas, along with anomalous methane and carbon dioxide ratios and temporal variations consistent with biological activity. The statistical probability, based on multiple independent analyses, exceeds 99%. We're as close to certain as science gets without actually visiting the planet. This isn't just one interesting discovery. It's a watershed moment for humanity. For the first time, we have strong evidence that life exists beyond Earth, not just in our solar system, where we might share a common origin, but 120 light-years away, completely independent, proving that abiogenesis, the emergence of life from non-life, happens multiple times in the universe. If it happened on Earth and K2-18b, it probably happened billions of other times. The universe is likely full of life. Most of it is probably microbial, like K2-18b. But given billions of planets with billions of years for evolution to operate, intelligence probably exists too. Maybe rarely, but in absolute numbers, there could be thousands or millions of intelligent civilizations in our galaxy alone. We haven't found them yet. That's the Fermi paradox, the mystery of the Great Silence. But K2-18b tells us they're probably out there somewhere. The implications cascade in every direction. Scientifically, we're entering a new era of astrobiology as an observational rather than purely theoretical field. We'll study more worlds, find more life, understand the diversity of biology across the cosmos. Philosophically, we're forced to reconsider human significance. We're not the center of the universe. We're not the only life. We're one instance of a common phenomenon, special to ourselves, but not cosmically unique. This could be depressing, or it could be liberating. Personally, I find it beautiful. The universe isn't dead matter mechanically orbiting in empty space. It's alive. Chemistry becomes biology given the right conditions, and the right conditions exist on billions of worlds. We're part of something larger, connected to life across vast distances. Participants in a cosmic story that extends far beyond our planet. Religiously and culturally, we'll adapt. We always do. Some traditions will struggle. Others will embrace this new knowledge and grow from it. Over time, the existence of alien life will become integrated into human culture the same way Earth orbiting the Sun did. Practically, this will shape space policy and research priorities for generations. The search for life is no longer speculative. It's a confirmed field with real discoveries to make. We'll build better telescopes. We'll study more planets. We'll eventually send probes to other star systems. Maybe in a few centuries, humans will visit K2-18b or worlds like it. But even if we never leave our solar system, we've made contact in a way. We've detected life. We know it's there. That changes everything. So what should you take away from all this? First, let yourself feel wonder. This is one of the most profound discoveries in human history. Don't let it pass by unnoticed. Appreciate what we've learned. Second, understand that you're living through a unique moment. The transition from wondering if we're alone to knowing we're not. Tell people about it. Share the excitement. Third, support the science that makes discoveries like this possible. Vote for science funding. Encourage curiosity. Celebrate achievement. We need more people who care about understanding the universe. Fourth, think about what this means for how you live. Does knowing about K2-18b change your perspective, your priorities, your sense of meaning? For me, it reinforces the importance of perspective. We're living on one small world among billions of living worlds. Our conflicts and concerns are real, but not cosmically significant. What is significant is that we're part of a living universe. We have the privilege of being conscious organisms who can understand and appreciate that fact. We should probably try not to destroy our planet. We should probably treat each other better. We should probably focus on building a civilization that lasts, because we're part of something bigger now. K2-18b didn't give us all the answers. It gave us better questions. It opened up a new chapter in human knowledge that will take centuries to fully explore. And you're here at the beginning of it. The universe is alive. We're not alone. Life is common, robust, and diverse. That's the message from K2-18b. That's what we learned from starlight filtered through the atmosphere of a planet 120 light years away. It's the most important thing humans have learned in a very long time. So the next time you look up at the night sky, remember, you're not looking at empty space. You're looking at a living cosmos full of worlds we're only beginning to understand. And somewhere out there, on a planet we call K2-18b, life exists. Different from us, unknown to us, existing without knowing we exist, but connected to us by the fundamental mystery of being alive. That's profound. That's beautiful. That's worth everything we invested to discover it. Thank you for watching. If this video changed how you see the universe, hit that like button and subscribe for more content about space, science, and the search for life. And drop a comment below. I want to know, how does knowing about K2-18b change your perspective? What does this discovery mean to you personally? The conversation is just beginning. Let's have it together. Until next time, keep looking up. The universe is more amazing than we ever imagined.